This is for Physical Science 102 for Tri-County Technical College. I'm TJ Lipinski. You're a professor. All right, so this is the textbook that we're using, which is called Conceptual Physical Science. The authors, Hewitt, and so forth. Anyhow, so we're going to start on chapter 13, which is in the middle of chemistry, although it really has more to do with, it is chemistry, but it's also nuclear physics as well. All right, so let's get right into it. So we're going to learn about several things, including radioactivity. All right, so these are the different topics that we're going to cover. Radioactivity, the atomic nucleus. We'll learn about what's called the strong nuclear force, and really the big thing there is how the strong nuclear force and the electric force work against each other, and in fact that's what causes radioactivity when they're not in balance. We'll get into that later. So we'll also talk about a term you probably heard about, which is called half-life, and that'll be one of our first equations that we use, is the equation for half-life. When I'm doing the PowerPoints, I will mention the equations, but then I'll do like a separate videos where I actually work out any kind of mathematical details with you. Make sure that you have a scientific calculator. That's really, really important. All right. Then we'll talk about what's called transmutation. And this was actually the dream of the alchemists, believe it or not, right? This was the idea that, you could somehow take some metal, some common metal, like lead, for example, and change it into gold. Well, nowadays we can actually do that. It turns out it's a lot more expensive, like incredibly expensive to do that. And it's just better, like if you want to find some gold, you just go looking for it in the earth. The next topic we'll talk about is radiometric dating. We use this for dating all sorts of things, from human remains to plants and other animals that died long ago. We'll talk about carbon dating, which is used for things that are in the maybe tens of thousands of years old. It doesn't really work very well beyond that. But then we'll talk about the radiometric dating for things like the Earth. How do we know that the Earth is 4.5 billion years old? All right, so that we use something that has a radioactive element that has a half-life that is starts to approach the age of the Earth. So you couldn't use carbon dating for the age of the Earth, as we'll talk about. All right. The next thing, because I think like carbon-14 has a half-life, like I forget exactly what it is. It's like around 5,000 years. All right. The next thing is nuclear fission. Right. So that this is a process of building. Not building really. Turning heavier elements into lighter elements. And when that happens, there is this release of energy. That release of energy, in fact, was discovered that although he wasn't really studying this, Einstein, of course, came up with this famous equation, E equals mc squared. We'll do some mathematical examples with this. What this stands for, E is energy. It's going to be in units called joules. The mass will be in kilograms. And c is the speed of light, and squared, you got to square. So the speed of light is 3 times 10 to the 8th, and the units are meters per second. So we'll do some really good examples with that, and we'll see how, turning a certain amount of fissionable material into how much energy do you get out of that, right? So that this is the equation that governs that, and then the final thing is nuclear fusion, which is kind of the opposite of nuclear fission. Nuclear fusion is when you take lighter elements and you bring them together, or you take a lighter element and you like hit it with a proton or something like that, or an alpha particle, as we'll talk about in a little bit, and you can make heavier elements, and that also releases energy. All right, so and of course we'll also talk about hydrogen bombs, which is a result of our ability to understand, our ability to basically use nuclear fusion. But another thing that we're graced with, as a matter of fact, is this is the process by which the stars produce energy. So that's another, and of course that's the topic that we'll cover towards the end of the semester, is the stars. All right, so let's start with radioactivity. And so the basic thing is, we got to remember that of course the periodic table of the elements. When we look at the periodic table, there of course are all these different elements, and all right, I looked for the periodic table, but I couldn't find one. Anyhow, it was very difficult to get one to appear. I'll show one in a little bit, or maybe in another video. All right, so anyhow, radioactivity that we encounter in our day here. Let me go back to this. So there's these unstable nuclei. Basically, the nuclei have. Is this where I was? Hold on. Let me just make sure. So yeah, the radioactivity. Okay. All right. So there's a certain number. Like in every element, there's a certain number of protons and a certain number of neutrons, and for most elements on the periodic table, there you can find a balance of protons and neutrons that will give you a stable element. And when you look at the periodic table, most of the elements that you look at are stable. All right. There are some, however, that are automatically radioactive, and radioactive just means that the number of protons and neutrons make it so that that the nucleus undergoes changes. Right, so that's kind of what we're going to be talking about, and so those, the general term for the nucleus undergoing changes is called radioactivity. Right, so that's the idea of radioactivity. The nucleus is going to change. Right, so and how it does that is kind of what we're going to talk about. Oops, can I maximize that? Oh, there we go. So sorry, I should have done that earlier. All right, so let's see. Yeah, so I just mentioned that. Let me just start off with one quick example. Let's take the element carbon. All right, so that's element 6 on the periodic table. I remember I was trying to show you a periodic table a minute ago, but this thing is not cooperating with me. Anyhow, carbon has six protons, and the normal carbon that you find every day, the run-of-the-mill carbon, is called carbon 12, right? Which is the 12 is the nucleon number, the number of protons plus the number of neutrons, right? So, carbon always has 6 protons. That's, in fact, the number of protons defines the element. But elements can have different numbers of neutrons. and the different numbers of neutrons are called isotopes, right? That's the idea of what an isotope is. So one isotope that we find in nature of carbon is called carbon-14, right? So carbon-14 is it is a naturally occurring isotope of you know, you don't find it, there's not very much of it out there, but it does occur in nature, and and uh, and so, you know, like for example, you find it in plants, you find it in animals as well. And so this thing carbon-14 has two extra neutrons, and that makes it unstable. Another way of saying unstable is it's radioactive. It's just naturally radioactive. Okay, so that's one of the things that we're talking about. And you can have you know, different elements that are. I mean, you can pretty much make any element radioactive if you add or subtract enough neutrons. All right, so it really is all about the neutrons, right? The protons, of course, are there. They're you know, in the nucleus, but there are neutrons, of course, in the nucleus as well. And really, what the neutrons are doing, in fact, are stabilizing this thing that we call the nucleus, the center of atoms. All right. Most radiation that we encounter is, as it says here, the natural background radiation that originates from the Earth and also from space, believe it or not. There's these things called cosmic rays, which are high energy particles and high energy electromagnetic radiation, like light, but much higher in energy than the visible light that we encounter every day. And so because of that, the higher you are, like if you live in Denver, Colorado, for example, the famous, you know, Mile High City, you are encountering, just by living there, more cosmic rays, because our atmosphere tends to block or it tends to block is a good word. Most of this radiation that is raining down from space. All right, but you know, the thing is, we're always in a bath of radiation, right? You know, it's you can't get away from it. For example, right? Think about like building materials, right? Bricks and cinder blocks and things like that. Those will inevitably have material in them, you know, not much generally. You don't normally build a building with extremely radioactive substances, but there's just naturally occurring radioactive material when you build bricks and when you build cinder blocks. It's just part of nature. And of course, the Earth has radioactive elements inside of it, in particular uranium 238, and there's no getting around that. So there's always this background radiation, but for the most part, it's pretty low. You know, if you think in terms of how much radiation humans come across in their daily lives. Of course, there are times when you encounter large amounts of radiation. For example, when you you know, go through a screen detector at the airport. You know, all right. So cosmic rays, as I mentioned before, there are two types. There's high energy particles. So these are subatomic particles, and they're moving really fast, generally really close to the speed of light. Not at the speed of light. That would be a violation of physics. But really close to the speed of light. And then, of course, you have this high frequency, high energy electromagnetic radiation, also known as gamma rays. That of course is again, this is pure energy. It is traveling at the speed of light. Gamma rays travel exactly at the same speed the same speed that red light does,